The title of this paper, "Attention is All You Need," isn't just catchy. It boldly states a revolutionary claim that fundamentally changed how we approach sequence processing.
It implies that the complex recurrent and convolutional networks, which used to dominate, might not be necessary. But how could that be? We covered the core idea of self-attention in case TCM 123001, but all of it?
This paper introduced a new architecture, the transformer. Crucially, it was based solely on attention mechanisms, dispensing with recurrence and convolutions entirely.
So it's not just using attention as an add-on, it's the only core mechanism. That's a huge departure from models like LSTMs or GRUs that built context sequentially.
And the benefits were immediate and substantial. By removing sequential recurrence, the transformer became more parallelizable and requiring significantly less time to train.
This is critical. Faster training means we can build bigger, more capable models more quickly, which unlocks new possibilities for AI applications.
On machine translation tasks, the transformer didn't just compete, it outperformed. For instance, it achieves 28.4 BLU on the WMT 2014 English to German translation task.
That's a concrete benchmark. A BLU score improvement of over 2 points is significant in machine translation, showing this wasn't just a theoretical win.
It wasn't a one-off success either. On the English to French translation task, our model establishes a new single-model state-of-the-art.
This generalizability is key. We've seen in cases TCM 033001 and TCM 063005 how transformers now generalize across modalities like vision. This suggests the attention mechanism captures a fundamental way to relate discrete pieces of information within a sequence or across different modalities.
Okay, so the results are undeniable. But if it dispenses with recurrence and convolutions, how does it maintain context and structure across the sequence? What holds it all together?
That's the core question. The answer lies in how attention is designed to build contextual representations at every step, creating a rich understanding of the entire input.
Let's break open this black box and look at the major components. We'll build up the intuition of how the transformer uses attention to process sequences.
I'm ready to see how it takes a sentence and without processing word by word, transforms it into something meaningful.
This illustrated guide helps us visualize the transformer, a model that uses attention to boost the speed of training. Think of it like a translation service.
So, we give it a sentence in one language, and it gives us the translation. That's a familiar setup like the encoder-decoder models we've seen before, but without the old mechanisms. However, unlike a human translator, the transformer doesn't understand meaning in the same abstract way. It learns statistical relationships between words and their contexts.
Exactly. At a high level, it still has an encoding component, a decoding component, and connections between them. This architecture provides a robust framework for sequence-to-sequence tasks.
Okay, so the overall structure isn't entirely new. The real magic, then, must be inside these components and their connections.
Indeed, the encoding component is a stack of encoders. Imagine layers of specialized processors, each refining the input sentence's representation, passing its output to the next. This analogy works for the sequential flow of information through layers, but unlike independent processors, each encoder layer shares the same architectural blueprint and learns to extract different levels of abstraction across the entire sequence.
Like a series of filters, each extracting more abstract features. However, these aren't fixed, predefined filters. Their behavior is learned during training, based on data through vector transformations. Does each encoder do the same thing, or do they specialize?
Before we dive deeper, there's a critical piece we need to understand about how the transformer handles sequence order. Since we've dispensed with recurrence and convolutions entirely, how does the model know if apple comes before tree or after? This is solved by ensuring we add positional encodings to the input embeddings.
So it's not just the meaning of the word itself, but also its relative position in the sentence that's encoded directly into the initial vector. This ensures that even though words are processed in parallel, their order isn't lost.
Exactly. These encodings give the model information about the position of each token in the sequence. It's like stamping each word with its location before it enters the attention mechanism, allowing it to preserve the sequential context.
Each encoder has two main sublayers. First, the encoder's inputs first flow through a self-attention layer. This is where the crucial process of context building happens.
Ah, self-attention. So within the encoder, each word's representation gets enriched by looking at all other words in the input, even words it usually couldn't see due to sequential limits.
Following self-attention, the output goes to a feed-forward neural network. Crucially, this network is independently applied to each position.
Wait, independently? So after the self-attention layer creates context, the feed-forward layer processes each position in isolation? That seems to contradict the idea of context.
That's a great observation. The transformer explicitly states there are dependencies between these paths in the self-attention layer. The feed-forward layer then acts like a local, position-wise transformation on the already contextualized representations.
I see. So self-attention builds the context, and the feed-forward network then individually refines each contextualized token. The initial analogy of filters holds up quite well here, but it's important to remember these filters are dense, nonlinear transformations applied to vectors, not visual filters on images. They operate in an abstract, high-dimensional space.
Now there's another crucial architectural detail in each encoder and decoder block. After both the self-attention sublayer and the feed-forward sublayer, we employ a residual connection around each of the two sublayers, followed by layer normalization.
Residual connections, often called skip connections, help propagate gradients effectively through deep networks, preventing vanishing gradients we discussed in prior cases. And layer normalization, that helps stabilize activations and speed up training, right?
Precisely. The residual connection helps information flow directly, preserving the original input while adding the transformation, and layer normalization regularizes the input to the next sublayer, making deep transformer models much more stable and easier to train efficiently. The decoder component also uses self-attention, but between its self-attention and feed-forward layers, there's another attention layer that helps the decoder focus on relevant parts of the input.
This must be the cross-attention, right? It's how the decoder looks back at the encoder's output, much like how attention mechanisms traditionally connected encoders and decoders.
So we have encoders that build rich contextual representations of the input, and decoders that generate output using self-attention and cross-attention.
Now that we have the overall map, how does this self-attention mechanism actually compute contextual representations, transforming isolated words into context-aware representations?
Let's consider the classic example. The animal didn't cross the street because it was too tired. Self-attention's power is that it allows it to associate it with animal.
This is crucial for understanding language. We learned in TCM 12301 that self-attention helps resolve ambiguities and build a richer, contextual meaning for each word.
The first step to calculating self-attention involves creating three vectors from each input word's embedding: a query, a key, and a value vector. These aren't just copies, they're derived by multiplying the original word embedding with three distinct learned weight matrices.
So every word simultaneously asks a question, offers itself as a point of reference, and provides its content.
It's like a lookup system, but with learned projections. Where it differs from a simple lookup is that there isn't an exact match. Instead, relevance is calculated as a continuous score, leading to a weighted average rather than a single retrieved item.
Next, to find out how much a word should pay attention to another, we calculate the dot product of the query vector with the key vector of the other words.
This is the core of the attention score. A high dot product means the query word finds the keyword very relevant, right?
After the dot product, we divide the scores by 8, the square root of the key vector dimension, and then pass the result through a softmax operation.
The division helps to stabilize gradients by preventing the dot product scores from growing too large and pushing the softmax function into regions where its gradients are extremely small, which would hinder effective learning. And softmax normalizes these scores into probabilities, meaning they sum to 1 and can be interpreted as relative importances or weights. So now we have weights indicating how much to attend to each word.
These softmax scores determine how much each word will be expressed at this position. It's not just a lookup, it's a weighted blending.
This refines our mental model from hashtag TCM123001. It's not simply finding the most relevant word, but intelligently interpolating information from all relevant words.
The fifth step is to multiply each value vector by the softmax score. This scales down the content of irrelevant words and keeps the content of relevant ones. So, the query and key determined how much to pay attention, and now the value provides what information to pay attention to. It's like who asks, what, who answers, and what's the answer. This analogy helps distinguish their roles, but it's not a conversational or query response process. It's a series of parallel vector computations.
Finally, we sum up the weighted value vectors. This produces the output of the self-attention layer for that specific word, a new, context-rich representation.
This vector now encapsulates not just the word's original meaning, but also relevant information from all other words in the sequence, weighted by their importance to it.
What we've just described is a single attention mechanism. The transformer doesn't use just one, it uses multi-head attention. This allows the model to jointly attend to information from different representation subspaces at different positions.
So instead of one blend of all relevant words, it creates several different blends simultaneously, like having multiple specialized detectors, each looking for a different kind of relationship?
That's a good way to think about it. Each head learns to focus on different aspects of the input. For example, one head might prioritize grammatical dependencies, while another focuses on semantic relationships. The outputs from these multiple heads are then concatenated and linearly transformed, providing a richer, more diverse contextual representation. This self-attention mechanism, repeated across multiple heads and stacked in encoders and decoders, forms the core of the transformer.
It's a powerful way to build context. But how did this architecture then evolve to become the foundation for so many advanced language models like BERT?
This parallel processing and contextual understanding are transformative, but it's not without its challenges. One significant aspect is the computational cost of self-attention. Because each word potentially attends to every other word, the memory and computation scale quadratically with the sequence length. For very long documents, this could become prohibitive.
So while it revolutionized shorter sequences like sentences, processing entire books with standard self-attention would quickly hit computational and memory bottlenecks. That's a crucial trade-off. Immense flexibility for context, but at a substantial cost for extreme lengths.
This paper introduces BERT,
pre-training of deep bidirectional transformers for language understanding. It's a direct evolution of the transformer architecture we just explored.
So BERT builds on the transformer, but what does bidirectional encoder representations really mean for understanding language?
Traditionally, language models process text sequentially, either left to right or right to left. BERT, however, leverages the transformer's ability to process all tokens at once to create a deep bidirectional transformer.
Ah, so it's not just about looking at words from left to right to predict the next word. It can consider the context from both sides simultaneously, across all layers, to build a richer representation of each word.
One key innovation for this bidirectional understanding was BERT's pre-training objective, the Masked Language Model, or MLM. Instead of predicting the next word, BERT randomly masks some percentage of input tokens and then tries to predict those masked tokens based on the full, unmasked context around them.
So it's like a fill-in-the-blank game, but played at scale during pre-training. This forces the model to learn deep contextual relationships from both directions to accurately guess the missing words.
In addition to MLM, BERT was also pre-trained on a next sentence prediction, or NSP, task. This helps the model understand relationships between sentences, which is crucial for tasks like question answering and natural language inference.
So it learns not just about individual words and their immediate context, but also how sentences relate to each other. This combination makes it a powerful general-purpose language understanding model.
The impact was staggering. BERT achieves new state-of-the-art results on 11 natural language processing tasks, establishing a new paradigm for NLP.
11 tasks. That demonstrates the power of pre-training a deep bidirectional transformer and then fine-tuning it for specific applications. It became the foundation for an entire generation of powerful language models.